Let me start. So my name is Ranjini. I'm a professor at the Raman Research Institute and I'm the chair of the soft condensed matter department there. So I work on soft matter, I do experiments, we also dabble a little bit in theory. So now how many of you know what soft matter is? Okay, Medhavi knows. Anybody else? I don't think you have undergrad courses on soft matter, but it's really something that comes out totally from classical mechanics, thermodynamics, and statistical mechanics. And it's material science, okay? We look at different kinds of materials, but we don't look at boring materials, we look at fun materials like all these. So you may not have heard of soft matter, but you would have, all the materials out here. So that's ice cream, that's a foam, that's sand, yeah, right? Yeah, that's a desert. This is a lotion, this is clay, okay? This is toothpaste, this is foam that's coming from shampoo, and this is paint. And my thesis today is that I can predict the properties of all these materials using some basic universal principles. Okay, they look very, very disparate, but there is common ground. Okay, so these are called complex fluids because obviously these are not simple fluids, they're like Newtonian fluids. Now, I know this is the last general talk, I think, so I'm going to have to keep you awake. I take my job very seriously, so I'm going to ask you questions. So what is a Newtonian fluid? So these are not Newtonian fluids, but first let's see what a Newtonian fluid is. Raise your hands and you have to give the answer. Please don't speak over each other. I mean, first, of course, you have to speak at all. Yes. Okay, I mean, I wouldn't call anything normal or abnormal. Okay, now, how many of you have heard of Stokes' Newton's law of viscosity? Yes? You're going to tell me Newton's law of viscosity? Okay, how many of you know Hooke's law? Hooke's law. Everybody knows Hooke's law. See, I mean, that's because in our minds, we think of elastic materials, solid materials. Liquid materials are equally interesting. So what is Hooke's law? Who wants to go first? What's Hooke's law? I saw lots of hands. I mean, surely there'll be people speaking out too. Thank you. So Hooke's law is a law that is meant for a perfectly elastic material, which says that below a critical strain, which is called an yield strain, or the strain required for permanent set, the stress that you are applying to a material is proportional to the amount by which it deforms. Okay, and what is the proportionality constant? That's the elastic modulus, right? So similar to Hooke's law, which is for elastic materials, there's a law for viscous materials. Okay, that is called Newton's law of viscosity. So Newton has come up with many, many laws. This is one law that unfortunately we don't really hear about. So this is actually Stokes-Newton's law. So Stokes-Newton's law says that the stress that you apply to a fluid, or the stress response of a fluid, is directly proportional to the rate of strain that you apply to it. Okay, so if you apply a force, say F sine omega t, then the response of the liquid is going to be something, okay, some strain, some amplitude, strain amplitude into cos omega t. Okay, so if you apply a force on an elastic solid, the strain is exactly in the response, which is the strain, is exactly in phase. But if you apply a force to a liquid, the strain is 90 degrees out of phase. Okay, these materials are neither. Okay, so for this Newton's law of viscosity, stress is proportional to shear rate or strain rate, and the proportionality constant is the viscosity. What do we understand by viscosity? Viscosity is basically the inhibition of a material to flow when pushed. Okay, so now obviously something that doesn't flow easily has a higher viscosity, right? But then viscosity of normal materials, as you said, normal fluids like water or honey or glycerol, they don't depend on how much you're pushing them. Okay, no matter whether you strain them at a like a strain rate of 1 per second or 10,000, 10 billion per second, okay, the viscosity is always the same, right? But in these materials, in all these materials, the viscosity, which you can calculate because they do flow under duress, okay, depends on the rate of shear that you're applying. Okay, so these are called soft materials or complex fluids because the underlying structures are usually very, very complex, which is why they are not Newtonian liquids. And so let's try to define them. They all look pretty different, right? So what is it that kind of, binds them together? Okay, so I'm not going to try to define it because, it was defined, I think the best as was possible by Pierre de Gennes, who got the Nobel Prize, okay, in 1991 for showing that the kind of theories that you can use to understand ordering phenomena in magnets or superconductors can also be used for describing soft materials such as liquid crystals. You all know liquid crystals, right? Right, so this is the theory is the theory of order parameters. So when he went to take his Nobel Prize, he had to give a little talk, the Nobel lecture, and this is how it started. What do we mean by soft matter? So see, this whole terminology, soft matter and complex fluids, it depends on which side of the ocean you're in. So if you're on the east of the Atlantic Ocean, we call it soft matter. On the west, they call it complex fluids. So, and Pierre de Gennes was French. So what do we mean by soft matter? Americans prefer to call it complex fluids. This is a rather ugly name which tends to discourage the young students, but it does indeed bring in two of the major features, complexity and flexibility. So all the materials that I showed you in the last slide, they are complex, they are structurally complex, as you'll just see, and they are mechanically flexible. Okay, so what do we mean by structural complexity? So you've all read quantum mechanics, right? You know that in the beginning of the 20th century, there was a lot of, people were looking at single ions, single atoms, single blah, blah, blah. Okay, but then gradually, people started looking at a huge, collection of them, like many body effects. Okay, so that is the structural complexity, just like, so life developed from a single-celled organism, right? And then, we evolved, we grew bigger and complex, and here you have me, right? So similarly, so that's structural complexity. So these materials that, we use every day without perhaps noticing them very much, okay, they are structurally very complex. But then there are certain things, okay, like weak interactions, self-assembly, spontaneous self-assembly that actually makes them tractable to experiments as well as theory. Mechanical flexibility. Now, what do I mean by mechanical flexibility? It's in the language of soft matter, what that means is you give a small push and you get this enormous response. Okay, and Pierre de Gennes, in his Nobel lecture, he described flexibility not really by mechanical flexibility, which is how I understand it because I'm a rheologist, but in terms of chemical flexibility. Okay, in any case, these materials are flexible, and this is the example that Pierre de Gennes gave. So he told us the story of boots that American Indians wore, okay, or Native Americans wore in the Amazon basin. Okay, so the Amazon basin is actually treacherous for leeches. Okay, but then, if you are a Native American there, you need to go into the forest and, hunt or, maybe, well, get perishables from the trees. So what they used to do to protect their feet from leeches was they used to tap rubber trees. There are lots of rubber trees in the Amazon forest, okay? And when you tap the rubber tree, something called sap comes out, latex, right? Latex is a polymer, okay, which is nothing but soft matter. Okay, so you can think of a polymer as, so a polymer it's a linear long molecule made of many, many small molecules repeating units called monomers, right? So you have these monomers that are these tiny, usually organic molecules, but then they can covalently link together to form these chain-like molecules, and that's polymer, okay? That's plastic. The plastic bags that you use, that's just a plastic, it's PEO, polyethylene oxide. Okay, so now this is what sap or latex also looks like. So you just tap a rubber tree, you put a bucket underneath, and you'll get this white milky fluid that comes out, that if you could look at the individual molecules or macromolecules, these are big molecules, under a microscope you'd see they look like this, okay? But then the moment it comes out of the tree, there's something brilliant that happens, okay? See, we think that the oxygen in the atmosphere is not reactive at all, but it is. Okay, so just, because these, so these polymers, they have nodes, which are basically, points on the polymer where the interaction is maximum. So now, just by, exposure to the atmospheric oxygen, another polymer chain will come in somewhere and, connect the nodes. Okay, so initially you just had these chains that were suspended in water, but now you formed a network. And like we all know, a network is more rigid than single chains, right? So the sap that they painted on their foot became a solid boot. Okay, so that is chemical flexibility. You know, what was a liquid became a solid, and by a rather inconspicuous chemical reaction, which happens spontaneously. Okay, so now there was a little problem with this. Now the same oxygen that helped make these connections also breaks up these connections. Okay, so an American Indian boot lasts for about 20 minutes or so before all these connections, they get chopped off. But then it took the genius of Charles Goodyear. How many of you have heard of Charles Goodyear? He manufactured rubber tires, okay, by a process called vulcanization. So then rubber tires, which they have stood the test of time, right? They were actually manufactured by the same process, okay? Except that rubber tires were made with latex but were boiled in sulfur, okay? And that made these bonds so strong, okay, that it didn't melt. Okay, so this was serendipity, and you see that soft matter is all about serendipity. Okay, so rubber is a soft material. Okay, it has chemical flexibility. But then because of this, reaction with sulfur, rubber tires last forever. At least we don't change the tires on our cars before, your car has gone, say, 50,000 kilometers or so. Okay, so that's mechanical flexibility, and let's come back to structural complexity. So now I'll show you the structure of one of these complex fluids or soft materials that I showed you in the last slide. It's something you see a lot. So this is about a micron or so. So this is an electron microscopy image. Okay, so it's basically light microscopy but with electrons, because you want to look at smaller scale structures. This is taken in RRI, my parent institute. Can you guess what this is? I'm sure you can't. It has glassy behavior, but no. So I want I'll give you options. Ice cream? No. No. Okay, what did we have? Foam? No. I mean, it has a hexagonal structure, but this is no foam. What? Shampoo? Lotion? This is clay. This is clay which is from the ground beneath your foot. Okay, so the soil that we walk on, the major ingredient is clay, right? So clay is a gel. It has this network structure. So if you put it, so this is of course, not the clay that we got from the soil outside, but this is some designer clay. It has the same chemical composition, but because we have to write research papers, we can't deal with muck. We use better samples. So this is clay under a microscope. It has a network structure. Okay, so clay is a macromolecule, so it has a supramolecular structure. It's not just like a hydrogen, oxygen like that. But clay has it's an inorganic molecule with it has oxygen, sodium, magnesia, silica. So it's a very complicated molecule. It's called a macromolecule, and these macromolecules, they are basically they have assembled. Okay, they've self-assembled under something. So Coulombic interactions, right? But given the charge distributions on these macromolecules, you don't have Coulombic interactions. There is electrostatics between particles, but Coulombic interactions, as you know, are very strong, and they decay to zero at infinity, right? But these materials, they have what is called a screened electrostatic interaction. So they do interact electrostatically. So positive will go and get attracted to negative, but it's a very short-ranged interaction, and it's a much weaker interaction. But anyhow, if you don't remember anything else, remember that this is what clay looks like under an electron microscope. You'll not see much under a light microscope. Okay, so there you go. So, but then, because of these very weak interactions that, bind these clay macromolecules together, it is fragile, okay? It easily breaks, okay? And that makes it soft. And if you look at the viscosity of clay, okay, as you increase the shear stress, you'll see that the viscosity decreases with shear stress. Okay, so this is called shear thinning, that as you're applying shear, okay, the viscosity goes down, so the material seems to have thinned. Okay, on the other hand, if you have a Newtonian liquid like water or oil or glycerol or whatever, the viscosity is always constant no matter what shear rates you are using. Okay, and I can also tell you, so I can just again, I drew some polymers here. So why are polymers elastic in the first place? So polymers are these, chain-like molecules. Now, in a polymer solution, you'll have many polymeric chain-like molecules. Now, these molecules, the energy scales are such that these molecules or macromolecules can actually entangle under thermal stresses. There's temperature everywhere, right? So you just take a few of these, molecules. They are not chemically reactive molecules, but you just put them in water. There's Brownian motion, there's thermal fluctuations, and these guys will all go and, they'll go and entangle. Okay, so now when you entangle, you again form a rigidish structure like this. Okay, but it's not a very rigid structure, it's a very fragile structure, because the same thermal energy that is producing these entanglements can also rupture the entanglements. Okay, so if you have polymers, okay, and it looks like this, but if you put them, if they are in a shear flow, which means velocity here is 0 and velocity here is whatever, then you're going to see that, because if the shear is high enough, you're going to see that all these polymers which were entangled, they get unentangled, and they're going to align along the direction of flow. Okay, and obviously you don't have a network anymore. So what that means is, it's not elastic anymore. Its viscosity goes right down. Okay? Okay, so these are self-assembled. See, I'm not taking them macromolecule by macromolecule and, producing this structure. But just because of the electrostatics on every single macromolecule, if you throw them together in water, this is the free energy minimum state. Okay, so you just take, different molecules, put them in water, and it's just going to, on its own, assemble and form this state. This is called self-assembly. Okay, but they are fragile. They are not very elastic, right? So they can actually break up just under thermal fluctuations, just in room temperature. So therefore, they can actually flow under small stresses. And these materials, because they have rigidity, yet you can also melt them by very small forces. They are called viscoelastic. So they are viscous and elastic at time scales that we can access. So how much could my graduate student, for instance, access? If I tell my graduate student that the dynamics are like very slow, it will take 3 years, she's going to kill me. Right? So then, these are materials which are fantastic to do work on, because the relaxation times of these materials is usually between a few tens of nanoseconds to a few microseconds. Okay, maybe even milliseconds. And these are time scales that we can very easily measure in the lab. Okay, it's not rocket science, but these are very good model systems as a result. Okay, so viscoelasticity, I just told you, so these are all soft materials. They are very, very different looking materials, right? So what's common among them? I told you, they are all made up of macromolecules. They can self-assemble. Okay, they also, to very small forces, there are huge responses. Okay, so why do I say that these are solid and liquid at the same time? Because the first one is sand, right? So if you take sand on your hand, okay, you make a pile of sand, it retains its shape, right? And that's what we've learned in high school a solid does, that a solid retains its shape. But what happens if you just part your fingers? The sand is going to flow right through, right? So the sand actually went from a solid structure to a liquid-like response just by under the very, very weak force of gravity. Okay, now granular matter is a very, very beautiful beast, and it's something we work a lot on, but I'm not going to cover it at all today. But I will cover much smaller macromolecules. So granular matter is what is called athermal. So they don't really, they're always out of equilibrium. They do not respond to thermal stresses. But I'll be mainly covering what are called colloidal suspensions. I'll tell you what they are, except that the materials, the structural units are much smaller than sand. Okay, so this is a liquid crystal. So I've been telling you that for these complex fluids, a small force gives a huge response, right? So this is a liquid crystal. It is in what is called a nematic phase. You know that the beautiful, the colors that you see on your computer screen, that's because of alignment of liquid crystals, right? So if you don't switch on the power, it's all black, dark, right? But you just put 5 volts and look at those colors, right? So you just need these tiny voltages to actually get them to align, okay? So small force, huge response. Paint, non-drip paint, okay? This is again, a poster child of soft matter. So have you ever wondered why paints are non-drip? and how you make non-drip paint. Because because you have your can of paint and you take it out, okay, and then you take the paint on the brush and you wipe it on the wall. But then if it started dripping, it would look awful, right? But then it doesn't, right? Now you need to see and you need to think, so why didn't it drip? Because when I took it in the brush and when I wiped it on the wall, it did flow. But the moment I took the brush off, it didn't flow, right? Why? Because the paint is made in such a way that it is shear thinning. So when you're shearing it with your brush, the viscosity goes down by many, many decades. But the moment you remove the brush, there's no shear anymore. The viscosity again goes back to the original viscosity. So it cannot drip anymore. And it's also made such that, paints should dry very fast. Okay, so but all these, to make a perfect paint, you need concepts from soft materials. Okay, I incidentally gave up a job in Hindustan Lever before I joined RRI as a lecturer 19 years ago. Okay, so fine. So okay, so those are the materials on my left column. Now the materials on these two columns, they are a little different from the materials on the left column. Okay, so the student who gave a talk on Janaki Ammal mentioned something called the eel strain. Who was that? Who gave the talk on Janaki Ammal? So what's an eel strain? Because these materials have eel strains. Okay, I'll tell you. I'll show you what an eel strain is. Okay, so for that, Iqbal has kindly gotten me some shaving foam and Colgate toothpaste. Okay, these are not materials that you do not know of. So all of you would have brushed your teeth in the morning, right? That's nice. Okay, so then now here, it's not flowing, right? I mean, how am I going to brush my teeth if it doesn't flow? Okay, so okay, but then what do I do to get it to flow? Right. So what did you do by pressing it? You're probably pressing it without thinking about it, right? So what you did was you exceeded the eel strain of this material. So I'm not going to press it because I don't want to make a mess here. But so next time you brush your teeth, think about eel strain. So now why does it flow when you're pressing it? Okay, you give it a little squeeze. Okay, that is because toothpaste is really a mishmash of all different kinds of polymers. Okay, so in polymers, as you know, they respond to thermal fluctuations. Therefore, when you squeeze it, or when not going to squeeze it, but if I did, the force that I'd be applying is a little higher than thermal fluctuations, right? So what I just did was I just completely broke up all the polymeric entangled structures that formed. But the moment you put it on your brush, it goes back to being as viscous as it was earlier, right? And then of course you brush your teeth and then it becomes a liquid again. Right? Solid, liquid, solid, liquid. You see how cool it is? Okay. And the thing is, I mean, much of soft matter actually happens in the kitchen. It's just that we don't look at it. Similarly, for shaving foam, this I think I'm going to make a mess. So my first postdoc at UCLA was on shaving foams. Okay. So we were actually, foams are very non-equilibrium. I'm not going to be able to go into it. But then it's non-equilibrium because, the structure is constantly changing under gravity. So the project I was working on was a NASA project. And the idea was that we are going to devise a setup to look at the dynamics of foam in microgravity. Okay, so I was in UCLA between 2001 and 2003, the space flight, it was a parabolic flight, eventually went up 2 years ago. But anyway, that's how space science works. So here, let me just do it on this. So I'm just going to, pour some solid or liquid. Right? It's retaining its shape. But then you can actually get it to flow like this, right? You can't do that to the table, can you? Yeah? So how did this foam flow? The foam flowed because of, so what is a foam really? A foam is really lots of bubbles, gas bubbles in a very little amount of water, right? So when I shear it or when I push it, okay, the bubbles are moving, okay? The bubbles move by a mechanism called stick slip. Okay, so when I'm pushing it, the bubbles basically they are deformable, right? They are gas bubbles. So they kind of, squeeze against each other and they deform and then eventually, stresses are building up locally. But, no material likes it because the free energy goes up. So how do they release the free energy? By rearranging. Okay, so all the deformed bubbles, they'll just kind of, wiggle around so that they are undeformed again. Okay, so I mentioned that the foams flow by stick slip. So, stress builds up and then releases. Do you know any geophysical situation where stick slip is very important? It's like it's a continent scale phenomenon which happens through stick slip. Earthquakes, exactly. So, see, you cannot go and do experiments with an earthquake because earthquakes don't tell you when they are going to come, right? But you can actually use foams in the laboratory to look at the statistics of stick slip motion. Okay, so these are fantastic model systems. Okay, so that was so much about yield strain. So I'll just kind of quickly go through this, that all these materials are constituted by macromolecules that share very weak interactions between themselves and can spontaneously self-assemble into fragile structures. The structures and dynamics are obviously not independent because there is a very, very strong coupling between the conformation of the material and its mechanics. Okay, and like I've already told you many times, and like you saw with the foam, and also you'll, I'm sure, notice with your toothpaste tomorrow, that very tiny forces give rise to disproportionately large responses, and some of these materials have finite yield stresses. Okay, so now we talk about solids and liquids and 4 states of matter and all that. What I'll try to convince you is that it's all Maya. Okay, I mean, it's all about time scales. Okay, it's all about relative time scales. So now, how many of you know of this pitch drop experiment? You do, right? So it's the third longest running experiment in history. So let me tell you, you all know what pitch is, right? Pitch is what they use to coat roads. It's basically polymers and bitumen. Okay, and it is what gives the roads its rigid structure, so you can drive your car on it, right? So now in 1927 in the University of Queensland, there was one professor called Sir Thomas Parnell who wanted to teach his students about fluidity and viscosity and all that. So he devised an experiment. So this is actually the real experiment. This photo was taken in 1990. So he took a funnel. You can see the size from this picture. Okay, and he filled it with pitch. Okay, now before he filled it with pitch, he also heated the pitch so that the polymers are kind of evenly distributed. And then he sealed the funnel. Okay, he sealed the stem of the funnel so that the pitch doesn't drip off, and he let the pitch settle for 3 years. Okay, so in 1930 they snipped off the bottom. Okay, now this experiment shows that pitch can also be a liquid. Okay, but then it's a liquid on very long time scales. So what happens is, see, pitch is a soft material. There are all these polymers and things that are there, but then under gravity, but because the interactions are very weak, the polymers or what have you, they actually start unentangling. They start flowing locally. And if you wait long enough, it will actually, the pitch will flow out of the funnel and make a drop here. Okay, and then eventually when the drop gets very big, it will detach and it will fall. Okay, so now this is what, 2023. Okay, so I don't know if you're reading the news or not, but this got the Ig Nobel Award in 2005. Do you know how many drops have actually detached since 1930? We're looking at 73 years. I'm sorry, we're looking at 93 years, 14 drops. Okay, so this is John Mainstone, who recently passed away. So I'm sorry, only 9 drops. I forgot. Okay, so only 9 drops have fallen. Now it might all seem very stupid, but what it does let you do is, from the flow rate of the pitch, okay, through this funnel over these so many years, they actually, I feel, calculated something that was really fantastic. So Poiseuille's law, right? Poiseuille's law. So they use the Poiseuille's law in the neck of the funnel because they know the volumetric flow rate, they know the size of the funnel, they know the length and the cross section and so on. They actually calculated that the viscosity of the pitch was 2.3 into 10 to the power 11 millipascal seconds. Now, what is the viscosity of water at room temperature? Who said that? Thank you. So at room temperature, fantastic. I love that. Okay, 0.89. We'll approximate it to 1 millipascal second. Okay, so pitch looks like a solid. We drive our cars over it, right? But it's actually a liquid with a viscosity that is 2.3 into 10 to the power 11 times the viscosity of water. Okay? So everything is a liquid or a solid. It depends on how long you're prepared to look at it. Okay? So if I mean, we lived for 500 years, you'd call this a liquid because it flowed. It's just that you had to wait much longer. Okay? So, yeah. So then, so to describe such flows, and the fact that the kind of the line between solids, liquids, and other states of matter is very blurry. It all depends on the time scale, right? So then there is a dimensionless coefficient, a dimensionless constant in physics or chemical engineering called the Deborah number. Okay, so this is, of course, I don't know, I mean, so Deborah is she was a prophetess of the Israelites. Okay, there's a lot of mention of her in the New Testament, and she said something pretty amazing. She said the mountains flowed before the Lord. Okay, so the Lord has been around for so long that the Lord would have, seen the mountains flow. Now, of course, I mean, I don't know if she was talking about rheology, which is the study of flow of matter, but I think she was, because, this is a very, very deep statement, and indeed, there's a whole dimensionless coefficient that is named after her. It's called the Deborah number, which is basically it is the ratio of the relaxation time of the material divided by the time over which you're forcing the material. Okay, so it basically, you understand what a relaxation time of a material is, right? So my relaxation time would be the time I take to travel a distance which is equal to my characteristic size. So if I'm a meter, how long do I take to walk a meter? That's my relaxation time. Okay, and the time scale of forcing is basically, how fast, or how slowly somebody is pushing me. Because, if I am walking slowly and if somebody pushes me at a, speed that is much slower than my walking speed, nothing really changes, right? I believe I behave like a solid. Okay, but then if somebody pushes me very, very hard or very, very fast, then I'm going to go flying off, right? So that's exactly what happens. So Deborah number. So this is a relaxation time divided by the forcing time. And this, I'm just showing you this by using silly putty. You know silly putty, right? So you can get it in book houses and, so silly putty is again, all polymers. So everything, a lot of stuff here is all, like mixtures of polymers. So now if you take silly putty and you take it in your hand, it looks like this, it's a sticky, gooey kind of a thing. Okay, so I actually asked this, so my coursework students, I make them do this sum. Okay, so I bring silly putty and then I just put it on over here. Okay, on the blackboard, and then I ask them to calculate the relaxation time. So an exam for graduate students is typically about an hour or so. So they watch it flow down and then they estimate a relaxation time. Okay, so the relaxation time of silly putty is about 20 minutes. Okay, so it's perfect for a graduate examination. So as you can see, when when Deborah number is very small, okay, which means that the forcing time, okay, is much is slower than the relaxation time of the material. You're giving the material enough time to flow. Okay, so the same material, depending on how fast you're pulling or pushing it, it goes from being a liquid to a solid. Now, these are things, it might look like, but these have a lot of applications. So one application that I can tell you about are, Kevlar vests that people wear during war. Have you heard of these? So see, this started, so, in Ramayana and Mahabharata, people used to wear these, iron vests, right? So that they don't, well, I mean, get killed. But then during the Iraq war of 2001, a particular company came up with this proprietary material called Kevlar. Kevlar is very, very light. Okay, so the vest, which was a plastic vest, was filled with this Kevlar material. And when something came at you at huge force, okay, so at huge force, therefore a low forcing time, so very high Deborah numbers, the Kevlar in the vest, it went from being a liquid to a solid. Okay, so and the response time is like, extremely fast. So you can be protected against, I mean, high impact attacks. Okay, so non-Newtonian complex fluids. So I kind of told you everything that, they are big and slow because they are macromolecules. So even though I showed you electron microscopy data, there's also a lot of work you can do under a light microscope. Okay, so They can be pushed easily. Distinctive physics, interesting at several length scales. This is something we work a lot on. I don't have time today. And they're also excellent model systems. So these are two things that we work on. We work on glasses. So for instance, glassy materials like the window glass that you have there, okay, there has been a lot of theories on glasses from 1960. But because the dynamics of the molecules in the window glass there are not susceptible to experiments, there are two different relaxations. They're either too slow or too fast. So it's difficult to capture them in the lab. So we make soft glasses. Okay, and whatever theories were written in the 1960s, it's only now that we've started verifying all of them in laboratory experiments. Okay, and convection was also something we worked on. Not going to go into that, but then yeah, so it's a very good model system because the units are much bigger, but in condensed matter systems, it's very difficult to, do laboratory experiments. You might have to go to a synchrotron source, or, the forces that you get, they are not even high enough to really look at the force response, right? But soft matter, there's no problem with that, okay? And also we make our own soft materials. We can make our own colloidal glasses or soft glasses or whatever. So we can actually engineer the properties so that the time scales are exactly the kind of time scales that we want. Okay, they are very, very compliant materials. So we joke that, I have a background in physics, but then we've practically become physical chemists now because we make macromolecules according to our wish. Okay, so anyway, so what are the kind of complex fluids that we study in the lab? So we look at foams. I'm going to start skipping because I think I should be done by in another half an hour or so maybe, right? Yeah, so foam is one thing. I told you I did a lot of work on that. We look at the non-equilibrium behaviors of these materials, okay? Polymers I told you about, okay? And I told you about polymers forming knots, but then the knots also coming off and shear thinning and all that. And do you know what this is? Micelles, right? So where do you use micelles? So micelles, as you know, these are amphiphilic molecules. They have a hydrophobic part and a hydrophilic part, right? So what's a very good, everyday use of a micellar system? Detergent, right? So how do you think they work as detergents? Time to wake you all up and get you off from cell phones. Yeah. Right? Right, so then you make micelles like this, right? So if you look at this picture, so we'll come to that. So I'll just kind of, give the intermediate explanation. So these are molecules with one part that hates water and one part that loves water. So when you throw them in water, all the water hating parts, which are the brown parts, they kind of, come together. But, this is a cross section, it forms a micelle. So it forms this, kind of a capsule with the water loving parts on the surface and the water hating parts inside. And then I have a dirty shirt, I put it in water, and then I put some, soap. What do you think is happening? Exactly. So the grease on the shirt is hydrophobic, right? But then see, for the hydrophobic, for the dirt on the shirt, the grease, to go into these micelles over here, you have to give a force, right? And that's the mechanical, that's why, we do this, we scrub, right? That's mechanical energy. But that mechanical energy is enough that, the grease from your shirt, okay, gets kind of attracted towards the center of the micelle. Okay, so there are, of course, also critical concentrations below which, you have detergent action, beyond which you may not get detergent action. But of course, the way these material detergents are formulated is so that, it works over a broad range of concentrations and temperatures. Okay, yeah. So that's one thing. And then there's something called colloidal suspensions. So colloidal suspensions is basically a micron-sized particle or many micron-sized particles, which is the dispersed phase, okay? It's a discrete phase that is suspended in a continuous phase like water. Okay, so one example is clay, okay, that I showed you about. So clay are basically these, these are tiny discs, clay discs, they could be anywhere between a few tens of discs. So, I'm talking about the diameter here. It could be, from a few tens of nanometers all the way to microns, depends on where you're looking at. So the clay that we have outside, it's called bentonite clay. Okay, so those are, very, very large size distributions, but these are all colloidal. Okay, so if you put them in water, they stay suspended because of Brownian motion. Okay, there are some other colloids that again, we use every day. One is milk. Okay, milk is a colloid of protein particles in a medium, blood, okay, your RBCs, WBCs in your, in plasma, okay. So these are all colloidal suspensions, okay, so they all have the same physics, okay. So now, because we don't have a lot of time, I thought, so as you saw, there's this huge range of soft materials. They are all viscoelastic. So in that, I mean, they're very predictable, their flow. But then I thought I'll choose 3 different systems. One of them you all know very well, that is cornstarch. All of you would have seen, pictures, YouTube videos of people running on cornstarch pools, right? So cornstarch is actually one material that we work on. So my student Palak, who finished her PhD last year, so she had basically she had 4 papers, okay, and 2 of them were on cornstarch, okay, different flow regimes of cornstarch and interfacial instabilities. I mean, so she used to do something called viscous instabilities. So, you see what happens when you push a less viscous material in a more viscoelastic material like cornstarch. So she got these beautiful patterns. These were all patterns that were generated by instabilities. I'm not going to be able to talk about that, but I'll just show you some fun stuff with cornstarch. Maybe I'll pass it around. And of course, cornstarch, I mean, I'm a huge fan of Dr. Seuss. So, cornstarch, of course, was first made famous by Dr. Seuss in his book Bartholomew and the Oobleck, where Oobleck is cornstarch. So, in his book, it was this green, gooey stuff that was chasing this guy called Bartholomew, and he had to protect himself and his empire from this Oobleck, okay? So that's Oobleck. And if you look at Oobleck, again under an electron microscope, this is what it looks like. Okay, so cornstarch, where cornstarch comes from? It comes from it's a polysaccharide, it's a starch that comes from the kernel of corn. Okay, so it just comes and then you dry it and you grind it, and these are what cornstarch particles are like, when they are finely divided condition. So these are very irregular, again, discs, okay, about 15 microns across. Okay, now if you take these cornstarch particles and put them in water, okay, their flow and deformation is very weird. Okay, now before I show you why, because it's our job to find out what flow behavior is like, we're going to do an experiment. So water here, right? I would like a volunteer if possible. Okay, so water here, and so I have about 100 ml of water here, and we are going to put inside about the same, volume of cornstarch. Okay, your name is? Shriya, I'm sorry, I'm an old person, I forget names. Yeah, so then, we're going to dissolve it, and you saw cornstarch, right? It looks like that, huh? So it's the exact same thing, except that this is Brown and Paulson that is brought from a supermarket. So it's still kind of liquidy, we want it to be a little more solid. So I'm going to add a little bit more, and I'm going to make a mess. I mean, if you want to do experiments, be prepared to make a mess. Okay, but clean it up, because there are other people using the lab, and it's not nice to leave a mess. So I think we're getting there. Put a little bit more. Okay, so a lot of cornstarch and a little bit of water. Everything seems to be dissolving. Okay, so the other thing about experimental science is what my supervisor Ajay Sood used to say, that 99% of your experiments will not work. So you've got to work 30 hours a day. At that time, of course, we felt like killing him, but anyway, it's true. Okay, so we'll need some more cornstarch. Iqbal, I'm opening your big box. Yeah, I was hoping to save it, but more. So now I think we have what we want. So you just saw what I did, just took water, took this from a supermarket, added a lot, and then, I have what we call a suspension. So it's particles in water. Okay, I just showed you suspensions. So now, maybe a little more. I'm never happy. Yeah, so, okay, now this has to work. So now what Shriya is going to do is, she's going to take this, which we made in front of your eyes, and you're going to first stir it very slowly and then really, really fast as you can go. Then you have to tell your friends if it feels any different. Very slowly, easy, right? Now go really hard. See, you can't move it. Okay, that is because, and this is what my bread and butter is, how viscosity changes with shear rate. So when she applied a very, very low shear rate, so you saw that those cornstarch particles were like discs, right? So with a very low shear rate, they actually all start aligning along the lines of flow. But when you start shearing it very hard, okay, then all the particles, they start jamming into each other. Because it gets turbulent, right? So particles are all just kind of crashing into each other. It becomes like a traffic jam. Okay, and as you know, if you've been in a very, very crowded bus, there's no space to move. And if you have no space to move, your viscosity goes right up. So it gets very, very hard to stir. It's okay.
Like the spoon, like the spatula is itself bending.
Exactly, it looks like the spatula, which is stainless steel, might actually break off. So thank you. Okay, so what I'll do is, while we continue, I'll just pass this. So you can just, go slow and then go really, really fast, and you'll see what I mean. And if you want tissue, we have tissue here. Okay, okay. So now as you do that, I'm going to show you some experiments. Okay, no, first I have to tell you, I told you actually, but I'll just, okay, now I put everything in my pocket, so now I have to take them out. Okay, yeah. Okay, got it, yeah. So, okay, so this is what is called the flow curve of cornstarch, okay? So here I've plotted the viscosity and this is the shear rate. So higher shear rate means higher speeds of stirring. So for very, very low viscosities, not much happens. But then, because, your particles are not really rearranging. But when you apply very large shear rates, the viscosity goes down. And that's why when you're going very slow, you can actually stir the cornstarch quite efficiently. But the moment you try, you get impatient and you think, okay, let me do this fast. Okay, I'm going to use a better word. I mean, you're kind of, you've hit a wall, okay? You can't move the thing. And that is because when you kind of stir it very hard, the viscosity goes up by many orders of magnitude, okay? It's good to be patient, okay? So now it will come round to you, but I'll show you some more cornstarch stuff. So this is what is called shear thinning, and this is what is called shear thickening. Okay, so now this is something that was done in our lab many years ago. So by my students Prakhyat and Rajiv, they all have permanent positions all over the place. So I've been around for a really long time. So then when we first thought we'll work on cornstarch, so so this is a Petri dish filled with a sample right just like this. And we wanted to give it some external drive. So what did Prakhyat do? He went to MG Road, which is a famous road here, and he bought a speaker. Okay, like a 2-in-1 speaker. And this black thing that you see, that is that speaker. So what he would do is, so what you see now, and thankfully without music, is that, some Punjabi music gets played. And so, you have this amplitude and frequency. Okay, so it's a kind of a sinusoidal thing, but, very high frequencies and high amplitudes. And look at this. So as you can see, I'm going to stop this. Or it doesn't stop, doesn't matter. But here, when I first started shaking, can you see the ripples? It's just like ripples on the sea. These are called Faraday ripples. So that is like the water behavior. Then what Prakhyat did, you saw him blowing into a hollow tube, right? So what he did was, he kind of, because of that force of the, the air, locally, the cornstarch, they started separating and aggregating. So the local concentrations became higher. Okay, and because of a higher local concentration and also this, the external forcing, it keeps jumping around. We call this a cornstarch monster. So, it all looks silly and fun and, but actually, you can do some theory on this. Okay, so, and believe it or not, this goes on for 20 minutes. Okay, so as long as you play the music, it'll go on. So this is basically the solid-like behavior of cornstarch that coexists with liquid-like behavior. Okay, and all you had to do was just to blow on your sample with air. Okay, so that's one thing. So that's from the lab, but there's something else that I kind of flicked off YouTube, and we'll go through this. So, okay, so let this go on, but we'll also, start the one on the right. Okay, so, Okay, so this is just a fun experiment. So I remember many years ago, this was a very common sight in ICTS, because ICTS keeps getting kids over to popularize science. So the most the favorite demo used to be a cornstarch pool. So people used to come out looking like ghosts, but anyway, it was a lot of fun. And a huge mess, of course. Then last year I organized a summer school on soft matter, so we had this prism workshop. So you could see people, there were like footsteps of cornstarch all over the place. But anyway, so they have this big bucket of cornstarch, okay, and now what he's doing is, okay, they put some more cornstarch and they made it thicker. You can see, right? I mean, it's kind of, disintegrating like a solid. And now they're going to jump on it. I can't see this thing, the scrolling thing. So I'm afraid we have to go through the whole thing. So you'll have to give me some extra time, I think. Okay. Yeah. Okay. So they're very, very, very thick now, and see what the children do. Okay. Now they're going to jump on it. Okay. So if you jump quickly, it's a solid. You can't do that with water, right? Yeah. Like a spring, which is what Hooke's law describes. So, you can jump on it and not fall through, but the moment you stand, there you go. Okay? Because, there's no forcing anymore, right? So your Deborah number becomes really, really low and you sink. Okay, actually, one of the materials that we worked on is actually, it's quicksand. Okay? So it has similar principles. Okay? We can make quicksand in the lab. I don't know, if you like, for me, the whole inspiration came from The Hound of the Baskervilles. I don't know how many of you have read it, but the whole thing is, quicksand is important. So we can actually, the plot can be recreated in our laboratory. So now there's material 2, that is an elastic polymer solution. You all know that, right? I mean, there are many, many elastic polymer solutions. One of them, for instance, is it could be idli batter or, egg, or, egg is basically nothing but polymers, right? Proteins and polymers, right? So something like that. So now we are not going to do it. I mean, I have videos because we do all this in the lab. But then I got some slightly more refined YouTube videos. But so here, you know what happens when you take a Newtonian liquid like water and you stir it, right? The meniscus is concave, right? It's convex downwards. So, and that is because of inertial forces. Now, what I'm going to, but now we have polymers, and this is what polymers look like. Okay, long chains, formed of monomers. This red thing is nothing. Don't let it alarm you. It is just a tracer particle. Okay, and then so you just do the same experiment. So instead of stirring water, you stir a polymer or an elastic polymer solution. Okay, it's called the Weisenberg effect. Okay, so this is, it's some polymer solution with some cross-linker. So it's rather elastic. So you're doing the same experiment, but look, it's going up, not down. Okay, now I'll tell you, I don't think I have a lot of time to explain it. If you're interested, I'll tell you why that happens. But we call them complex monkeys. See, because the fluid actually climbs the rod. Okay, just, completely inverse of what you would expect with water. Okay, so then, the first one was some polymer with, a low cross-linker concentration. The second one was, I think, pancake batter. Okay, so this is pancake batter. So, you could shear it, but it doesn't go up much. Or maybe I should tell you what is happening. So see, when you are stirring it, so you have lines of force, right? But here the lines of force, there's also some elasticity attached to them. So they are really like rubber bands. And you know what happens, like, right, with rubber bands, they're always trying to shrink. Right? So that's exactly, and there are some liquids, which are very elastic. Just, look at it, versus the ruler. It will go all the way up. Okay, so how much it climbs is also something that you can control, right? So now, all this was fun and games, I agree. But then, I thought, just to show you that, you can actually do work that is, that you can identify with, but then also from which work that has predictive powers. Okay, from soft matter concepts, I thought I'll show you some very recent work that we did on something that is very familiar, the cracking of soil. Okay, so we cracked soils in our laboratory, okay, and then we tried to predict where the first crack will form. Okay, so you can always see when the first crack is happening, and I'm a rheologist. I look at the flow and deformation of matter, so I like calculating elasticities. Okay, so I'll show you with experiments as well as a scaling theory that we came up with, how there's a very beautiful correlation between how, where, or when the sample cracks and what its elasticity is. Okay, so our lab is called the Rio DLS lab. We do many things, but it's just called the Rio DLS lab. But so this is work that I did with my grad student Vaibhav. He's fantastic and he's about to finish, but this is the experiment that he set up. Okay, so we are just air drying clay. This is a very simple setup, you know, it was like made from scratch in our workshop. So we have a big box. Okay, so this is the big box and we put our clay here. So this is the clay sample, it's red because we put a bit of dye. We put a bit of dye so that the cracks are visible. So the cracks are visible because, you know, it's a very thin layer. So when it cracks, you can see the substrate. Okay, it's a Teflon dish. So, you know, you see the moment it cracks, you can see the white Teflon underneath. Okay, so that's what we define as a crack. So he keeps it on a weighing scale, but I'm not going to get into all that. But he just looks at it, you know, so he illuminates the clay from below. It's a transparent dish, and then, you know, he captures images with a video camera from up there, and that's it. Okay, and you just wait for the crack to form, and because you want to do a controlled experiment, so we have a temperature sensor. So we have a relay sensing that keeps the temperature controlled and the relative humidity control. So much of the controls happen through Arduino. I don't know, maybe some of you, you know, have you done Arduino programming? Okay, I see one hand, two hands, yeah. Very, three hands, very powerful. Okay, so we do a lot of Arduino because, you know, it gives us very nice control. Everything happens from the computer. Okay, and we just wait for it to crack. The relative humidity is actually controlled by a very archaic technique. We just keep a supersaturated magnesium chloride salt solution. Okay, so it just maintains the relative humidity at 27%. So this is the Petri dish that, you know, this camera sees from top. So just watch this. Okay, so it's actually a 14-hour video. Okay, that has been compressed to 9 seconds. Okay, but the only thing is, you know, so for the first few hours, nothing happens. The cracking really happens around, I think, 14 hours or so. Okay, so I think what you see here is between 10 hours to 24 hours in 9 seconds. So keep a keen eye. So you see, so the crack started developing at the walls. Okay, the first crack developed at the wall, then it started propagating tangentially to the boundary, and after that, you know, you had these, so these are called circular cracks, and then eventually there are these radial cracks. Okay, so now desiccation cracks form near the wall of the Petri dish, that's all good. So then how do you record the time of onset of the crack? Okay, so it's simple. So this is again my dyed solution. So we have to do a little bit of, you know, jugglery, image jugglery. So then, you know, we grayscale it, we find the binary. So these are all the same images, but only kind of, you know, doctored. Okay, and then, you know, the cracks. So then, you know, the red looks black, and then, you know, the cracks are the white, which is really the substrate that you're seeing, right? So then as the cracking process happens, we monitor the substrate area, which is the white portion. So then we wait, and then after some time, you see that the, you know, the white area becomes non-zero, and that is my crack onset time. Okay, that is when the cracking started. And now we've of course done this experiment, or rather Vaibhav has done this experiment for all kinds of samples with different amounts of salt. Salt makes a sample more elastic. And also when you increase the concentration of the clay, it also gets more elastic, and more the elasticity, the faster it will crack, right? So this is what we see, that the crack onset time, which is, you know, like plotted versus the salt that you've added. Remember, salt makes the sample more elastic. It decreases with increase in salt concentration and also with increase of clay concentration. Okay, so that's one thing, and that's easy, that's just visualization. But what we did next was slightly more non-trivial. So we have an atomic force microscope that many of you might have heard of. So what it does is, it's a cantilever, okay, and it comes and interacts with the sample, and as a result of the interaction, the cantilever, these are nanometer sized cantilevers, they deflect. Now by looking at the deflection of the material, of the cantilever, as it contacts the material, you can actually measure the elasticity of the material, okay? So this is done, I'm not going to get into details, but this is done in what is called contact mode. So you're really taking the AFM probe, the cantilever, and you're pushing it into your sample, okay? And then you're seeing how much the cantilever is deflecting, and from the deflection of the cantilever, you can calculate a force displacement curve, like you might have seen for Hooke's law. Okay, so again, not going into details. So we get force displacement curves, which we fits to something called a Hertz's model. No time for details here, but then it lets us extract the elasticity of all the different samples whose crack onset we looked at. Okay, so then again you see that the elasticity, I mean this was known, but now we have real numbers that the elasticity of clay increases as you increase the concentration of clay as well as the concentration of salt that you've put in the clay. Okay. Okay, now we want a simple model. I mean, obviously this is a very, very complicated system, and it's just, it would be a little bombastic of us to even try to reproduce everything, right? But then we thought, let's see. So, how should this crack onset time change with the elasticity? So the reason why I'm showing you all this is because, I just want to tell you that, as fun as these materials are and as common as they are, you can actually solve differential equations and learn a lot about them, and you can actually learn enough about them that you can predict their behavior. And if you can predict their behavior, you can also change compositions. You can engineer these materials so that you can get them to do the things that you want them to do. If you want to stop cracking, you can do that. Okay, so now this is the model. So you heard a lot about the diffusion equation, I think in Abhishek's talk and then in Rajaram's talk. So chemical civil engineers mainly, they use the same diffusion equation for a drying gel. Okay, so this is called a poroelastic model, and what it describes is, so a poroelastic gel is basically a saturated deformable gel medium with water in the pores. You saw in that gel picture, right? There were big pores. That's not empty. That has water, right? But then because of evaporation at the surface, the water molecules, they are diffusing through the pores. Okay, so that diffusion is being described by this diffusion equation, which is called it's the theory of poroelasticity. Now civil engineers don't call it a diffusion coefficient, they call it a consolidation coefficient, because as the clay dries, the water leaves the system, kind of settles down vertically. It's called consolidation. Now, as that happens, as the system becomes, settles vertically, okay, as it consolidates, there is a meniscus that develops between the particles. It's a colloidal suspension, so there are many particles. Now, as the curvature of the meniscus increases, from Laplace's law that the pressure goes up a lot. Laplace's law, everybody knows, right? Yeah. So the pressure at the surface is very high. So this is the pressure that we'll try to find out. And that pressure, now because of this whole evaporation process, that you develop these pressures on the top surface that is actually more than the pressure at the bottom, okay, you develop a stress in the plane of the evaporating surface. Okay, so we want to solve this equation to see how P goes, to solve for pressure, which is the pressure within the pore. Okay, so I'm not going to go into a lot of details, but then as you know, when you have a differential equation, to solve a differential equation, you need boundary conditions, you need initial conditions. So we have used all that. So the boundary condition is really what is called Darcy's law. I mean, that is, that tells you how flows happen in a porous medium. Okay, so we call this a porous medium because it's a gel, right? There is the material and then there's the pores, right? So it's porous. So like I said, I'm not going to go into that. Then we put the initial conditions. We say that the stress is proportional to pressure, and then we can actually calculate the stress at the evaporating surface. Okay, H is the thickness of the sample, and we see that the stress, so this is all by solving this, it is proportional to the elasticity of the material, it is proportional to the time at which you are measuring the stress, it is proportional to the rate of evaporation, and it is inversely proportional to the thickness of the layer. Okay, so now this was our solution, and we followed a paper that was already published to do all this. But now interestingly, so I've just written the same thing that we solved, our solution right here, but the C is critical, okay? So what this means is TC is the critical time, that is the time of crack onset. Okay, now sigma c would be the stress on the surface of the material, okay, at which the first crack will form. And the first crack forming basically means that this is the first time that you're creating two new surfaces, because a fracture is nothing but creating two new surfaces, right? Now, fortunately for us, we already know how, the kind of potential energies that you need to create two new surfaces. This is given by what is called the Griffiths fracture criterion, which tells us that the critical stress for fractures to start is proportional to what is called a fracture energy, the elasticity of the material that is fracturing, and divided by pi, and A, which is the thickness of the crack. Okay, so then we basically put the sigma c here, and then we do a little bit of algebra, and you see that the crack onset time should go inversely. I mean, this is the slope of the curve, of course, should go inversely as the square root of the sample elasticity. Okay, and here's our data and here's our fit. So what you see here, all the black points here, these are our experimental data. Okay, so this is a crack onset time that is plotted versus 1 over root over elasticity. So remember, the crack onset time we measured by direct visualization, and E was something that we measured using our AFM technique, right? And this, so black are the experimental points and blue is the theory. Works beautifully. Okay, so the reason why I showed you this is because, see, the theory that we've used, I don't know if you noticed it, but it's one dimensional. We were only looking along Z, but even though it's one dimensional, so, and also remember, clay, the elasticity is not constant, because clay, it's constantly, there's solvent loss. The elasticity is actually increasing. But in spite of all this, we do this really, really simple model and it works. Okay, so it's not just fun. Okay, there are also predictability. So now, I have these samples. Now what about a sample right here? I may not be able to make it. I may not be able to, measure it in an AFM, but I just need to extend this fit, and I can tell you that, when the crack will onset, right? I can now tell you that if I want to make a crack resistant film, okay, I need to make sure that the elasticity is so much, right? Because I have this scaling relationship that I can use. Now on the flip side, so as you can see, this I have the straight line fit, right? Now the slope of the straight line fit is this piece here, right? And from the slope, I can calculate this GC, which is what is called the fracture energy, to be 1000 joules per meter square. And for somebody who works on materials flowing and breaking, this is a very nice number, because it tells me exactly what category of fracture this is. This is what is called ductile fracture. Okay, you know what ductile fracture is. So, when you throw a stone on glass, what you get is brittle fracture. It'll just shatter, right? But in ductile fracture, it's an elastic medium, yes, but when you try to apply a force to make it break, the underlying structure tries to resist that breaking. So it will deform, it will do all kinds of stuff, and it will really try to resist the fracture, but then eventually it fractures. But it's a slow process. So clay shows us ductile fracture. So that's my third material. I just showed you this because this is all very, very, research that is going on right now. We are actually writing it up, okay? But so this is a very simple experiment, really. The theory is also very, very simplified, but it has predictive powers, okay? We can guess how materials will behave, and once we can guess how materials can behave, we can also make new materials, okay? So now that's about the talk that I wanted to tell you, but if any of you found soft matter interesting, I would ask you to read these books, because as you see that, these are very, very, ubiquitous materials. We see them all the time. So there are these, actually both of them are my colleagues. Okay, so this is this beautiful book written by Roberto Piazza. Okay, so it's called Soft Matter, the Stuff That Dreams Are Made Of. Okay, so he really talks about the structure, dynamics, phase behavior, and how, you should be looking at, when you go to the kitchen, there's soft matter everywhere. Okay, and there's also something beautiful that he says, and captures very well in his book, that physics should be made simple enough to be amusing, but not so trivial as to spoil the fun. Okay, that's why I decided to show you our clay work, that this is all serious stuff. Okay, the second book is by Michel Mitov, another colleague. He's now in Nice, okay, called Sensitive Matter. So this is really about physics in the kitchen. Okay, the mayonnaise, how to make good mayonnaise, how to make good tomato sauce. These are all soft materials. Okay, so read the book. It's really beautiful. Okay, and because I can't stop boasting about my colleagues, I also have to tell you about an ignoble award that one of my colleagues from UC Riverside got. Okay, so I already told you about so these are all the ignoble awards, that I could think of, that went to soft matter experiments. Okay, I told you about the pitch drop experiment. Unboiling a boiled egg is something that my friend Greg Weiss did in UC Riverside. So he actually boiled an egg and unboiled it again. Okay, and he got the ignoble in 2015. So as you know what the idea of ignoble is, right? Ignoble awards are given to experiments that first make you laugh out loud, but then they make you think. Okay, because it could all seem very ridiculous, but there's a lot of information you're getting out. For instance, like in the pitch drop experiment, you actually calculated the viscosity of pitch to be 10 to the power 11 times higher than the viscosity of water. Had you not done the experiment, you would not have got that number. So in unboiling a boiled egg, what Greg and his team did was that, they boiled an egg. Now the egg white actually in this paper, so as you can see, it has come in a proper, like a dignified chemistry journal. So yeah, so they boiled an egg, and the egg white is nothing but polymers. Okay, so once you boil the egg, okay, the water that is there, it all evaporates, and all the polymers, they form this congealed mess. Now this congealed mess, as you know, for all those of you who eat boiled eggs, you can't think of it going back to that liquidy form again, right? But he could get it back into the liquidy form, and what he did was, once he boiled the egg white, okay, he put some urea in the egg white, which is organic. You may not want to eat urea, but anyway, so he put it in the egg, and urea is very slippery. So it goes to the nodes of the polymers and makes it slippery, and then he spun it very, very hard. Okay, and all the polymeric particles, the polymeric chains that constitute eggs, they all came apart. So the egg unboiled. Okay, so this paper that you see here, he got the Ig Nobel Award in 2015. So this was with egg white. And so, you'll see his YouTube videos. It's really very good. You must see it. Greg Weiss, University of California, Riverside. Okay, after that, he's also unboiled the yellow. Okay, sorry. This was the yellow. After that, he's also, no, this was the white. After that, he's also unboiled the yellow part. And on the rheology of cats, so this is, I had a special request from Disha there. So, that cats are viscoelastic. Okay, so there you go. So you can have a cat. So this is a proper paper, okay, in a journal called the Rheology Bulletin. So cats can jump like springs, but then they can also go and, fill any container. Okay, so he actually has, so you can look at the paper, it's available freely online. So he's actually, so there are many ways in which we calculate, estimate numbers that tell us about the elasticity and viscosity of the material. I'm done. Right? So he's actually calculated all the numbers. I'm not showing you any. So he's got the Deborah number, relaxation time, everything. Okay, so it's actually a 3-page paper. You should have a look at it. Okay, so it's fun, but then I've also, said it's also useful because it helps us, understand how materials work and also to engineer new materials. So I'm done. So acknowledgements, my fantastic group, of course, who makes every day, going to the lab every day, a lot of fun. I learn a lot from my students. Okay, my colleagues, friends, mentors, RRI for being very for being very graceful with money as well as other funders and with laboratory facilities. Okay, and this is my group from a few days ago, and we all have fun. So this is during an annual day where we, set up experiments for school students, and research is fun. Plus, I would ask you all to do, get PhD degrees because you get to travel a lot. Okay, so you get to travel a lot. I have traveled a lot, and it's been most enjoyable. So here you see me. About 8 years ago, I spoke to science ministers at a G7 conference. Okay, so yeah, so I got tweeted about, thank you, by the ministers of science of France, and it was all very cool. So then. And actually, somehow I also got on their mailing list because when her name is what? Najat something, the French Minister of Science. So somehow when she resigned because her party lost the election, I even got like a, bye, I'm glad to have met you kind of an email. Yeah, all that was very exciting. Okay, so you get to travel a lot and, It's lovely to be able to go to new places and meet new people. It, increases, it enhances your perspective of the world. It makes you a better person and well, at least definitely a broader person. Plus, you get to meet many new people like Nobel laureates. So this is my picture from 18 years ago, okay, at ICTP Trieste with Pierre de Gennes, who got that Nobel Prize that I told you for soft matter in 1991. So questions, this is my email address. Thank you so very much for your attention because I know we ran quite late. Thank you. Questions? Yes.
Hello. Yeah, I have two questions. So, is it appropriate to say that for non-Newtonian liquids, so if the shear stress is high, then Reynolds number is high because of the turbulence, and if it's less, the shear force,
That
that
is fair
Reynolds
to
number.
that is fair to say. See, but I mean, there's a lot of work on things like elastic turbulence. Okay, so where you can see for if you look at liquid. So I don't know if you know what Reynolds number is. Do you know what Reynolds number is? So Reynolds number is basically the the ratio between the inertial and the viscous components, right? Because the viscous component is going to try to stop the flow. The inertial component tries to make the flow turbulent. So high Reynolds number means turbulent flow, right? So in water, for instance, you can set up turbulence at, say, a Reynolds number of 10 to the power 5. But in elastic polymers, like I showed you, you can actually set up turbulence at Reynolds numbers that are as low as 10, 20. Because of the complex interaction. So yeah, very good question, yeah. So it is true that, but given a certain material, if you hit it hard, yes, the Reynolds number would of course be higher. See, but these are viscoelastic. So it's not just, storage, there's also dissipation. So it depends on the material. That's why, see, you can engineer these materials to do things that, you want them to do. Yes.
Second question is that in desert, when drought is there, they form polygons, right?
Salt
So,
polygons, yeah.
yeah.
Wow, that's nice. Okay, so yes.
Yeah, so
Finish your question. Yeah.
why they form polygons?
So that's a very good question. And actually, I have so many colleagues. So a colleague from Nottingham Trent called Lucas Goring, who actually works on this. Okay, so see, when lakes, these are saltwater lakes. Okay, so then when saltwater lakes dry, okay, that gives rise to a convection. Now the salt being heavier, they deposit. But because of the size and the nature of the convection rolls, they form these salt polygons. So that is because, see, one thing I told you was that these materials, they form patterns. So that is one example of pattern formation because of evaporation. What I showed you with the clay, that was another kind of pattern because of evaporation. So that's all well known now. Actually, you can actually theoretically show that you'll get polygons.
Oh, okay. So we can derive using formula. Okay.
In one dimension, like
Okay.
I did.
Okay.
See, these are very complicated systems. You can't really, get all the features out. Okay, so you can look him up. So he's called Lucas Goring in Nottingham Trent University. So he has these very nice, he actually has a very nice review article. So not just this, there are also other geophysical processes. Like you have something called columnar joints. Okay, so columnar joints are, these rocks with, these columns. It's very weird, It's like a normal rock, but with these, like ridges. So that also is a pattern that happens because if, evaporation of water inside, that was there maybe, at the time of the formation of the rock. So yeah, so pattern formation you can write theories for, but do not expect that you'll get a very accurate and precise theory. You can just get qualitative features. Yes,
okay.
working now.
So you talked about the cornflower and how the Deborah's number was changing. How do you see, you explained how the particles like the colloids, they first they squish and then all of that. How do you, is that theory or can you
We
see
don't
that
see.
happening?
See, we don't see. So what I showed you was just for fun. But if I can get 2 minutes, I can show you what we do with it. Okay. So this is not even part of my talk. But so, so cornstarch, these are what are called granular materials. And, so, in the industry, for instance, you have slurries, right? Granular slurries. Okay, you need to push out the slurries. Now that's a bit of a pain because of something called a viscous instability. Wait, let me show you. Okay. But maybe if you come down, I can show you. So then what we really do is that Yeah, so what we do is, so you push out a slurry. So you know about, say oil recovery processes, right? Do you know how they recover oil from rocks? So some rocks are very oily, okay? But they have so rocks are porous media and they have oil in the pores, okay? Now you want to extract that oil. What do you do? Huh? Do you know? Anybody? You push in air. Okay, so because when you push in air, the air basically pushes the oil out. Okay, but it doesn't push it out homogeneously or isotropically. It forms fingers. That is because when you have a very confined geometry, when you have a very narrow geometry, and when you try to displace a material in a narrow geometry, okay, then you form an instability. Okay, so I know these are just words, but what that means is when you try to recover oil from rocks by pushing out air, you see that the air is not propagating homogeneously or isotropically, it forms fingers. You can come and I can show you fingers. It's not working here. Okay, so this is what Palak looked at. That was like half of her thesis. So what happens when you when you push out shear thickening cornstarch? So whoever has the cornstarch you would have seen, right? It shear thickens when you shear it hard, but it shear thins when you stir it slowly, right? So the kind of viscous instabilities that you get when cornstarch is in the shear thickening regime or in the shear thinning regime, when you're pushing it out with a less viscous medium. Okay, you can actually write equations of motion for them. So we didn't do it in this case, but then we have collaborators in IIT Madras who do something called linear stability analysis. Okay, so doing linear stability analysis, you can actually predict that what will be the spacing between two fingers, for instance. So these projections that you get, these instabilities, they are called fingers. Okay, now the distance between the fingers, it's called the wavelength of the fingers. Okay, so obviously from our experiment we have a wavelength because we are seeing it, right? These are big centimeter sized fingers, so you not miss them. You don't need to look at individual cornstarch particles. We are really looking at what are called the emergent phenomena at larger length scales. Okay, we have no wish to look at single particles for the experiments that we do. You see, so then you do linear stability analysis and you can show that yes, under these conditions, the wavelength that you get, it is exactly that your theory predicts. See, it may be no use. I mean, who cares what the wavelength is? You push out your slurry, you push it out. No matter what but the thing is, it just feels wonderful that, you can put a number to it. And these are very complicated systems. So one thing that you have to understand is, the art of approximation. It's not just, doing experiments in soft matter, but no matter what you do, you have to make, intelligent estimates because, right? So I have students, for instance, so we calculate something, say a volume fraction, which is the fraction of colloids in water. So initially, I don't allow them to do this beyond like one day, but anyway, so they'll write, volume fraction is 0.789534. I mean, you don't write so many significant digits, right? So you need to know how many significant digits are important. You need to have that intuition, write only those, right? So, estimation is very important and, you get better and better at it as you do research. And also, I mean, like I said, and like you, I'll just come to you, like you pointed out, I mean, it's opaque, right? So how do you image them? But the kind of experiments we do, the kind of problems that we choose, we don't need to image them. You see? So we just kind of model it like a kind of a continuum medium, which is elastic, and we can manage with that.
You were saying like the colors we see on a laptop and TV is because of liquid crystals. Could you explain a little more about that?
So see the laptop screen, it has optical components, polarizers, analyzers, and all that. But it also has electrodes on the sides, right? So when you're switching on the laptop, okay, there is this electric field that is across your screen, which is of course very, very narrow. Okay, I forget. I think it's a few tens of microns. Okay, so now when you put the electric field, okay, so these are, as you know, liquid crystals are these tiny, nanometer-sized cigar-shaped molecules, but they can, they can flip. So then, these are birefringent materials. Okay, so depending on the electric field, which depends on the trigger, the signal that you are giving, they'll flip accordingly, and because they are birefringent, you see the colors. So now the beauty is, you know, you don't need huge fields to make this happen. Like 5 volts is enough, you know. So it's basically 5 volts over, say, a millimeter or so.
When we like take a video of like a laptop or something, we can see colors in the photo that we don't see with a naked eye. Is it because something to do with the liquid crystals?
Maybe
moving?
it's the, yeah, maybe, you know, it's the response time of your, you know, site versus, you know, the camera that you're using. Yeah. So see, these things are all kind of calibrated so that, you know, it works for normal day-to-day use, right? Yeah, there's a lot going on. So that's the beauty, you know, that, I mean, there's so much going on, but eventually, you know, you see the colors. But you don't see how the colors are coming, you know, and the response times are very fast. Your eyes will not catch it, but something else might. Okay, so then thank you again for your attention. Bye-bye.